Today, under statistical thermodynamics, we will be looking at the topic that is thermodynamic probability. Now, this thermodynamic probability for a given macro state, it may be defined as a total number of ways by which a given micro state can be realized. So, for a given macro state, how many numbers of micro states are possible is known as thermodynamic probability, and this thermodynamic probability is represented by Wp, or in many books it is represented by omega. So let us understand by taking the example that we have seen, that is, suppose in Ludo, if I want number 5, then this could be obtained by either 3 plus 2, 2 plus 3, 4 plus 1, or 1 plus 4. So these are the 4 ways in which I could obtain 5. So this individual combinations are the micro states, and 5 is the macro state. So for this particular macro state, in how many different ways a micro state could be arranged, so that is known as thermodynamic probability, and the total number of ways we could obtain 5 is 4. So the thermodynamic probability is 4. So this is for smaller number, and we have to use the concept of permutation and combination to in order to obtain the larger number. Suppose if we are considering that we have n number of identical and distinguishable systems, say suppose if I am considering that I am studying hydrogen gas, then hydrogen gas means hydrogen gas, all the molecules, they are identical, and suppose if we say that if I am labeling that for one molecule as Ha, other as Hb, other as Hc, so all these molecules will be distinguishable. So if we have a system having identical particles and they are distinguishable, and suppose if we are considering that it is the total energy of the system at constant volume and the temperature of the system, and if we are considering that they are arranged in this particular manner, that is n0 number of particles are distributed in E0, n1 number of particles are distributed in E1, n2 are distributed in E2, and ni are distributed in EI, then for such a system the total energy will be given as n0 into E0 plus n1 into E1 plus n2 into E2, and so on, and the total number of particles n will be given as n0 plus n1 plus n2, and so on. So for such type of distribution, the thermodynamic probability is given as n factorial divided by n0 factorial, n1 factorial up to ni factorial, and that we could write it as n factorial divided by capital pi of ni. As we are writing summation, for multiplication we are writing as ni. So this is for the system that is non-degenerate. For degeneracy, suppose if we are considering that G0 is the degree of degeneracy, or we can say this is the statistical weight factor, that is energy level E0 has degeneracy of G0, energy level E1 has degeneracy of E1, energy level E2 has degeneracy of E2, then these particles will be, suppose energy level E0 has degeneracy 2, so these particles could be arranged in both of those levels. Similarly, if energy level E1 has degeneracy 3, then this N1 particle could be arranged in all these 3 states, and so on. So we need to consider the permutation of these states also, and hence for thermodynamic probability for degenerate system is given as W is equal to G0 raised to N0 upon N0 factorial, G1 raised to N1 upon N1 factorial, and so on. So this is the thermodynamic probability for the degenerate system, and hence we could also write thermodynamic probability is equal to capital pi of Gi raised to Ni upon Ni factorial. So this could be written in this particular manner also. So this is for degenerate system and this is for non-degenerate system. Thank you.